And we're back from a little break. So I've had a think, and I think what we're gonna do is we're gonna try and actually move and rotate this little triangle. See if I remember any of my math. So this is where it's gonna get interesting. Because this is probably where you're gonna see me not having any clue of what I'm doing. Math was a long time ago. Anyways, so to do this, we're going to start with sort of like a model transform, which is what we transform our currently wonderful red triangle with to sort of rotate it. So what we're going to do is we're going to start with our vertex shader here, and we are going to introduce another sort of variable, but this time it's not going to be an attribute, it's going to be what's called a uniform. So sort of the way you think of this is that attribute is a per vertex thing. So there's one vertex coordinate per vertex, surprise, surprise, whereas a uniform is per model or per, yeah, in a galaxy far, far away, or per rendered objects of some sort. And we're going to do a matrix 4x4, and we're going to call it model transform. So in theory, the way I sort of remember this is that you just multiply them together. Now, which direction they're multiplied together to is always the interesting question, but I do believe it's like this. Whether that is actually valid GLESL, I don't really know off the top of my head. But we'll find out. Looks like my browser has decided to be a little bit annoying. Anyways, let's just see what we can do because I happen to have a GLSL quick reference as well, which is wonderful. So here you sort of have this. Let me just transition over so you guys can see it as well. So you sort of have the storage qualifiers here. We'll also get into varying at some point. Yeah, so that's kind of it. Here we go. There are row vector times matrix linear algebraic multiply and matrix times column vector algebraic multiply. So it is the correct syntax for it. But this is the point where I really have to think. Is this a column or a row vector? Because I might be... You know what? And so let's see. I vaguely remember it being this way around from... I did some OpenGL 2.0 way back. I vaguely remember it being this way around, so we're gonna assume that. And probably it'll show out to be very wrong, but that's just the way it goes. So given that, we need to access it. And this is done through, there are some GL uniform calls somewhere. They apparently weren't important enough to get into this. Anyways, that's sort of what we're going to be going for. And this will probably fail horribly. Yep. Just making sure everything works as it did a moment ago. Okay, it doesn't really, CMake doesn't really understand sort of the assets folders. It doesn't know it has to recompile stuff. At some point I should probably get that set up correctly. So that at least works. And I've managed to screw my undo buffer, so let's just write back in the uniform mat4 model transform. And we'll multiply that on. There we go. Just clean that for me and file. Reload here. So that kills off most of it. So what we want to do now is that we have this like get attribute location. There is also a set of calls called something like GL uniform. Here we go. Uniform matrix for FV. Requires a location. So what we need to do is we need to get uniform location here. Again, we're going to be using this shader program. I probably want to go down here. For this shader program, I want to get the one called model transform. Okay, and then with that, I want to say GL uniform matrix for FV. So the for FV is for float vector, and the vector means that I'm pointing it at an array rather than just writing all of them. So we are just going to save this as a GL int model transform location. So we're going to do the model transform location, and it's already forgotten to tell me what my parameters are. I prefer it when it does that, so I'm just going to do that. So I'm looking at the model transform location. Count is 16 elements. Transpose GL false. I don't think I want it transposed. And then we'll just have a model matrix here, which is also GL floats. Model matrix. I need a semicolon there. So we're just going to start with like the identity transform first. So we do absolutely nothing to it. So if I have anyone in the audience who's never done matrix math, this is an identity matrix. When you multiply it with a vector, it does absolutely nothing. So sort of the way you model this is if you imagine you sort of have your input vector lying up here and an output vector down here. So the x-coordinate of the output is 1 times the x-coordinate of the input plus 0 times the y plus 0 times the z and plus 0 times the w-coordinate. Is sort of the way you can visualize this. That's really the simple way. If we reload, we still got no triangle. I was kind of hoping that we'd get the triangle back by doing that. So, why did we not get the triangle back? What happens if we don't multiply this on? Just clean it because I need to do that for the... We got a triangle. So odds are we're multiplying by something crazy. Would be my guess. Just trying to make... At some point I'm going to learn not to push the run button. Either that or I'm going to set it up so that it reloads the page, which would probably be the sneaky thing to do. So, question is, what are we multiplying with? Because we're probably doing something really, really crazy. So, yeah. Sorry, my browser's doing weird stuff with me. Where for some reason it's not really updating stuff. Just a second. So with that done, I'm gonna quickly close those, and I want you to capture, where is it? That one. There we go. Now my browser works for me as well. So the GL uniform, this is sort of like the basic one, whereas if I'm doing vectors, here's the matrix one. This is the one I'm trying to use. Specifies the number of matrices that are to be modified. Yeah, I only want to modify one matrix. I really have to get used to the idea that this is counting and not sort of the size of things. Much better. So our triangle's back. Now we are gonna try and do a little bit of rotation of this. So what I want to do is I want to have a static float, which is gonna be our static float, which is going to be our time we initialize to 0. And then every tick I want to add our delta time to that. And then, let's see. This is, for rotation matrix, this is like a floating point cosine. Yeah, I'd like to pull that in from math. Of our time, and this is going to be in milliseconds, so to try and avoid it spinning at like the speed of light, we're probably going to do something like that. Now the same factor goes here. Then this one becomes a minus sign. So yeah, right now, for those of you who weren't expecting this from game development, it's matrix math and trigonometry. Could it get any better than that? With any luck, we will now have a rotating triangle. And it's probably not going to... Yeah, exactly. And because of the way our coordinate system is set up, it looks a little bit weird as it rotates. It looks very weird as it rotates. But that is actually how it should look, surprisingly enough. So, to sort of avoid this distortion, we should set up a projection matrix as well, which is sort of how do we map our world space into this. So we have this sort of concepts of different spaces. World space is sort of everything that you render, and that needs to get projected down to screen space, which is sort of the XY coordinate system of the screen. So what we should do is we should set up a projection matrix for that. So what we're going to do is we're going to add a projection transform. And that's just multiplied in front. That's the way it works. Nice and simple. So for this one's going to be a little bit more nasty. Because, yeah, projection matrices are nasty motherfuckers. So, called projection transform. I'm going to pull that out. At some point, this is going to be refactored so that it becomes nice, but right now, we just want to get it working and get a basic shader running. So, for projection matrices, these are nasty. There used to be, or I think it might be in the OpenGL utility library, yeah, GLU perspective. This is a wonderful function call. Unfortunately, it does not exist. So yeah, this is what happens. You specify a field of view in the y direction, you specify an aspect ratio so that you get the field of view in x direction. Then you specify as near clipping plane and a far clipping plane, and then it generates this matrix for you, where f is this wonderful cotangent here. So this is going to be a joy. So we're going to calculate this on our own. So we're going to do, I think what we're going to do, because this thing doesn't really change, is going to be, we could in theory do this very early on, but right now we're just going to do it here. So I'm just going to sort of specify these things so that we don't have to worry about them. Actually, we're going to do it as const expressions, which is a wonderful C++ 17 edition. Allows the compiler to do some calculations at compile time so that I don't have to do it at runtime. So our y field of view is going to be 60 degrees. I am going to hate myself in a moment for doing that. It is actually going to be m pi divided by 3. Also known as 60 degrees in radians, because the world works on radians, and such is life. Constant expression, aspect. So, oh yeah, need to tell you types of these. These are floats. So the current aspect ratio we have is a 16:9 aspect ratio. It's the ratio of the width to the height, so this is 16 point float divided by 9 point float, because I am not going to do that in my head. So a near clipping plane, how close does stuff have to be before we cut it off? We are going to cut it off at, this is where it gets a little bit interesting, because right now we're rendering our triangle at a z index value of 0. Problem with that is that our camera is conceptually at z index 0. So we can't really show that once we sort of specify a near clipping this plane. So what we can do is we can use our model transform to move our vertex. And let's see if I can remember the OpenGL coordinate system. I think it's something like you're looking down negative z. So we have to move it down 1 by negative z, and this element here in the model transform specifies how much you're moving along the z-axis. And then we're going to clip at 0.1, and we are going to clip again at, let's say, 10 float. Great, so now we can calculate that wonderful expression f, which is the cotangent. Oh, dear God, I don't think C++ has a cotangent function. Please have a cotangent function, otherwise I'd be really, really sad. So the answer is no, there's no cotangent function. So cotangent is equivalent to cosine over sine. So what we need to do is we need to say cosine, and we want the, oh yeah, C++ overloads these wonderful stuff. So we want cosine of the above divided by 2 over the sine of the field of view divided by 2. Great. So cotangent is cosine over sine. Then we can do our projection matrix. First, we have f over aspect ratio, and then a lot of zeros. Then we have another bunch of zeros, where we then have f. So these sort of just map the x and y coordinates in a semi-natural kind of way. Then what we get here is we do z far plus z near over z near minus z far. And then this is kind of interesting. We do 2 times z far times z near over z near minus z far. So this part where we're sort of affecting this last fourth coordinate based on the z distance is where we're sort of adding a scaling component, so to speak. So as how to explain? It's sort of it offsets a little bit of our z distance so that we move the z near plane here to be at 0 and the z far plane to be at 1 in our sort of space that we're working with. And then down here we do this, and this causes our whatever z distance we have, it's going to be divided by at the end, because you get sort of 4-dimensional vectors out of this, but you can't really display a 4-dimensional vector on a 2D screen. So what it does is it takes the x and y coordinates and then divides them by the w coordinate. So by taking the z coordinate and moving it negatively into the y coordinate, you get this effect where the further down the further down the negative z coordinate you are, the more you're going to divide by, so that you sort of get this narrowing effect, which is what you want to do with projection, or with like this kind of 3D projection. So we're going to try and see if that builds. It does not, because I've forgotten a type specifier here. So cosine is not a constant expression. I'm a little bit disappointed. I was expecting cosine and sine to be constant expressions. Maybe they are in weird circumstances. Let's try and see what happens. We're displaying nothing. Nothing is always the best thing to show. Did I get something wrong with this matrix? See, now comes the fun part. Figuring out what you did wrong when you have absolutely no way of debugging. Because I have no clue. So we agree that, yeah, MPie is a double. I know that. By the way, best set of constants ever. So we're taking a vertex, multiplying onto the model transform, multiplying it onto the projection transform. And that's our final position on the screen. So, what goes wrong here? Aspect is 69. Move that what was